So hello everyone, welcome back you all on another video on digital signal processor. In the last video of analog to digital converter, we have seen the architecture of analog to digital converter, where we have discussed the different mode of operations, that is 16-bit mode and 12-bit mode, SOC, start of the conversion registers, trigger selections, channel selections, acquisition prescaler, and interrupt sources. So in this video we are going to see the different set of registers for implementing the analog to digital converter using Code Composer Studio. So the first we will look at the different set of registers. What are the different set of registers to configure the analog to digital converter modules and its feature. Further, we will look at the practical implementations using Code Composer Studio. So if you haven't subscribed my channel, please go and subscribe the channel. Let's begin with the video. So the analog to digital converter module for the launchpad is having the different set of register, that is the control register 1 and the control register 2. Where the control register 1 will control the ADC operations such as enable and disable the ADC, setting the clock sources and selecting the conversions mode, whereas the ADC control register 2 configure the ADC operating modes including resolution, sampling rate and power down modes, where SOC 0 to SOC 15 control register will configure the control each SOC's configure trigger sources, channel, sampling window and other parameter for each conversions, whereas the interrupts SOC selection 1 and 2 registers will select which SOC generate the interrupt. Interrupt X and Y selection register configures the interrupt sources for each interrupt channel, and SOC priority control register will define the priority of each SOC for simultaneous trigger. SOC burst control register will control the burst mode operations including the number of conversions in the burst and trigger sources. The offset trim register will adjust the offset of ADCs to improve the accuracy, whereas the ADC register 0 to 15 store their digitalized result for each conversions. ADC interrupt flag will generate the interrupt pulse generated, and ADC interrupt clear register is used to clear the interrupt, whereas ADC interrupt overflow flag will be indication of overflow flag is generated, whereas ADC of interrupt overflow flag clear will be indication that overflow flag has been cleared. So now we will look at each register in detail, and we will see how to configure the analog to digital converter for the launchpad. This is the first set of control register, that is ADC control register 1, and it is shown that it is 16-bit register where 0 and 1 bit is reserved. The second bit is interrupt pulse position generations. It indicates that when this bit is 0, that means interrupt pulse generation occurs at end of the acquisition window, and whenever this bit is 1, that means the interrupt pulse generation occurs at end of the conversions. The second bit is the ADC power down mode, and that will be active low. This bit controls the power up and power down of all analog circuitry inside the analog core, and when this bit is set to 0, that means all analog circuitry inside the core is powered down, and when this bit is set to 1, that means all analog circuit inside the core is powered up. Next bit is the ADC busy channel, and further it is have the ADC busy. So depending upon the busy ADC busy bit, this channel will be defined. So this bit is defined. If the ADC busy bit is 0, that means that when this bit is 0 0, so for example, when this bit is 0 0 and ADC busy is 0, in this case, in this case, the last channel converted was the ADC in 0. So when the ADC busy is 1, so when the ADC busy bit is 1 and the channel is 0 0 and channel is 0 0, that means this channel is being processing. The next set of register is ADC control register 2, where the bit number 15 to 8 are reserved and bit number 7 is signal mode. Signal mode will be either how you want to configure the ADC. That means either you want to configure the ADC as a single-ended mode or the differential mode, and what will be the resolutions. Either you want to use the ADC as 12-bit mode or the 16-bit mode. Further, here the prescale is the dividing the ADC clock, dividing the input clock, and the input clock is 200 megahertz, and to achieve the ADC clock we are dividing the input clock divided by the number of prescalers, so to get the corresponding clock for the ADC. So for when you are writing this on the Core Composer Studio, we have to write the ADC set mode, the ADC channel and its resolutions, and the signal mode. So for example, if you are using ADC-A and its base is ADC-A, so you have to write the here ADC-A is the selected ADC module. Resolution is the you want to use the ADC resolution is 12-bit mode, so you have to write here 0, and the signal mode you want to use as a differential signal or single-ended. I am using the single-ended mode, so we can use the 0 in the signal mode. So this will set the ADC, it will configure the ADC, where the configuration will be signal mode, resolution, and the prescale. So once you configure the ADC, you have to use the trigger selections, channel selections, and acquisition prescaler. So trigger selections means how the ADC module is going to trigger, how it is going to start these conversions. So it can start the conversion based upon the trigger selection register. So you can configure the trigger with the help of CPU timer 1, CPU timers, CPU 1 timers, and CPU 2 timers. Other than that, it is having the facility for EPWM. With the help of EPWM module, you can trigger the analog to digital converter. So for example, if you want to trigger the analog to digital converter with the help of CPU timer 1 and timer 0, you can write 0 1 in the trigger selections field, and the channel selections bit, which channel you want to use. If you are using the single mode or a single-ended mode or differential mode, so in the SOC control register 2, if you have selected the signal mode is 0, then you have to configure like this, and if you have configured the signal mode is differential, you have to configure like this. So we have configured the signal mode is as a single-ended mode, then we have to use the channel selection as like this. So I'm selecting the channel number 1, so I'm writing here 1. Next is the acquisition window. The acquisition window means how many clock cycle our ADC is going to convert the analog signal into the digital data. So that will be always the calculated clock cycle, calculated time minus 1. So that will be ACQPS So that we will look at in the subsequent slides, how to calculate the equation prescaler, and how you are configuring these registers. So for example, if you want to trigger, so how you are configuring the ADC. So example, if you want to trigger the using CPU timer 1, you have to write ADC A register dot ADC SOC A CTL, because we are using the ADC A module, so we have to write here A CTL dot trig selections equals to 1. That means it will select the CPU timer 0. So now for the channel selections, what we have to write, we have to write the ADCA register dot ADC SOCA CTL dot CHSEL equals to, if we are using channel 1, we have to write as 1, and if you are using channel 2, we have to write as 2, depending upon which channel you want to use. Next is ADC interrupt trigger source select register 1, and so the ADC interrupt trigger source select register 1 will be defining that which SOC need to trigger, how the SOC will be going to triggering. So for example, if we are using SOC 0, so how the SOC 0 is going to be triggered, so that will be using, either that can be triggered by the triggered field register that we have defined previously in the trigger field. Other than that, if you are writing this bit as 0 0, that means that no ADC interrupt will trigger ADC. Triggered selection field determines SOC trigger. So if you are writing 0 1, that means this SOC will be triggering using ADC interrupt 1, and if you are writing 0 1 here, that means ADC interrupt 2 will trigger the corresponding SOC. So in this case, the trigger selection field will be ignored. So this is the way you can trigger the analog to digital converter SOC. The next is SOC priority control register. So here the bit number 9 to 5 is having round robin pointer that points to the last converted round robin SOCs and determines order of the conversions. If this RR pointer value is the 00, that means that SOC 0 last converted and SOC 1 is having highest priority. If this is 01, that means SOC 1 is converted and SOC 2 is highest priority. Whereas the SOC priority will be determine the cutoff point for high priority and round robin modes. When this SOC priority register value is 00, that means round robin mode for all channels. Then if this value is 01, that means SOC 0 is having high priority and SOC 1 to 15 are in round robin mode. When this value is 07, SOC 06, 02, SOC 6 is having the high priority and SOC 7 to 15 is having round robin mode. Now the next register is ADC burst control register. So here you can see that to using the burst control register, we have burst mode, we have to enable the burst mode. So to enable the burst mode, we have to select this bit as either 0 and 1. 0 means disable and 1 writing 1 means it is burst mode is enabling. So you have to write 1 on this register to enable the burst mode. Next you have to define the size, burst size. What will the burst size? So it determines how many SOCs are converted when sequence is started. And SOC burst trigger sources means what will be the triggering for the SOC burst mode. Further, the interrupt selections X and Y register. Here, the interrupt selection register, you can see that the interrupt selection register is the ADC interrupt X/Y EOC source select. That means that writing 03, that means EOC3 is triggered for ADC corresponding ADC interrupt. So for example, if you are using ADC interrupt 1, so it will be ADC interrupt 1. If you are using ADC interrupt 2, so it will be ADC interrupt 2. Writing to this bit to 8, that means EOC 8 is triggered for ADC interrupt 1. Further, this AD interrupt X enable, for example, if you are using the X equals to 1, then ADC interrupt 1 interrupt enable. So you have to enable it by writing this field as 1. Then ADC 1 continuous mode enable, that means writing 0 means one short pulse generated until flag cleared by the user, and 1 means pulse generated for each end of the conversions. So this is the ADC conversion register that will be in the 12-bit mode, and in the 12-bit mode the MSB will be this part and the LSB will be 0, and in the 16-bit mode the MSB will be this. So if you are giving the particular channel as a 3 volts, then the digital results will be FFFF, and for the 12-bit mode the results register will be storing these values. If the input voltage is 1.5 volts, then value will be, digital values will be this, and the results will be storing in these registers. So in a single ended one input pin will be there, and external reference will be V reference HI and V reference LO will be available, and that can be driven from the external voltage sources. In the 16-bit mode, the data will be on the 15 bits to the 0th bit, that is 16-bit data, and when the input voltage is 3 volts and the input is 0, the positive pin is having 3 volts and negative pin is having 0 volts, the results will be FFFF, and that will be storing in this register, and it will be 1111. And when input voltage, positive pin is having the voltage of 1.5 volts and negative pin is also having the voltage of 1.5 volts, it is having the output is 1 0 1 1 1 1 1, and all pin will be 1. When input voltage is 45 microvolts and positive pin and negative pin is having 3 volts to 45 microvolts, so the digital results will be 1H, and the results will be like this. And if positive pin is having 0 volts and negative pin is having 3 volts, the corresponding results will be 0, and the result register is having these values. So differential channel is having 2 input pins, that is the one is the positive pins, another means the negative pins, and the input voltage is the difference between the 2 pins. And here also external reference is needed to drive the analog to digital converter. So analog to digital converter is having the another set of register, that is the ADC interrupt flag register. So what is this ADC interrupt flag register will do? So the ADC interrupt flag register are total in 4, so that is ADC interrupt 4 to ADC interrupt 1. So the flag register for the ADC interrupt 4 will be indicating that the reading these flags indicate if associated ADC interrupt flag was generated since last clear. So reading 0 means that no ADC interrupt was generated, no interrupt pulse generated, and 1 means that ADC interrupt pulse generated. So how to clear these ADC interrupt flag register? So this can be cleared writing the ADC interrupt flag clear bit to 1. So by writing ADC interrupt flag clear bit, this interrupt flag can be cleared. There is another ADC interrupt overflow register. So what is the functions of ADC interrupt overflow register? So ADC interrupt overflow flag indicates its overflow occurred when generating the ADC interrupt. So whenever the ADC interrupt was generated, the overflow occurs. If the respective ADC interrupt flag, so we have generated the ADC interrupt flag. If the respective ADC interrupt flag bit is set and the additional EOC is generated, and during that time the EOC is also generated, then overflow conditions is occurred. So when this bit is equals to 0, that means no ADC interrupt overflow event detected, and whenever this bit is equals to 1, that means overflow condition is detected. The overflow bit does not care about the continuous mode bit state, and overflow condition is generated irrespective of the mode selections. Then how to clear these overflow conditions? So the overflow conditions is clear using the ADC interrupt overflow clear register, and writing this bit to 1, that means the overflow flag is being cleared, and writing 0 means there is no actions. If the software tries to set this bit in the same clock cycle, the hardware tries to set the overflow bit in ADC interrupt overflow. Then hardware has priority and ADC interrupt overflow bit will be set. So these are the basic set of registers for the analog to digital converter. So the one question can come in your mind that how to handle the signed integer values. If your input voltage is ranging from minus 1.5 volts to positive 1.5 volts, so how to do this? So for this you have to make an arrangement of the analog circuit. So from the analog circuit you can use some kind of op-amp circuit, some adders, and your input signal is having ranging from minus 1.5 to 1.5. You can add the offset to this one, so your signal will be 0 to 3 volt range, and this signal will be, you can feed into the unity gain amplifier, that is using that can be made using op-amp circuit, and that you can give to the ADC input pins. And in the microcontroller, whatever result registers you are getting, in the result register you can subtract the offset. So here offset will be 1.5 volt, and the 1.5 volt corresponding to 0x7FFF. So we have defined the offset equals to 0x7FFF, 07F, it will be 07FF, it will be 07FF for the 12-bit mode, and the offset you can subtract from the actual results, so you will get the actual output, that is 1.5 volts to minus 1.5 volt. So in the next tutorial we will be looking the step-by-step guide to initializing the ADC register in the Chord Composer Studio, and we will demonstrating the configuring the key parameters like resolution, acquisition window, and trigger sources. And we will see the examples of single-ended and differential inputs configurations, and we will build a simple projects that we are reading the values from the voltage and potentiometer or sensors and displaying it on the serial terminal or the LCD, and we will demonstrating how to debug ADC readings using breakpoints and watch window in CCS, and we will be implementing the oversampling mode capabilities using the Chord Composer Studio. So stay tuned for the next video. See you in the next video. Thank you.